So I'm Nicole McFarlane, and I'm presenting on sort of improved signal-to-noise ratio across a spectral range for CMOS silicon photomultipliers. And so I'm presenting, so I'm the professor, and so my students are the ones that have really done all of the measurements for this work. And so really what we're trying to do is what we want to do is replace the photomultiplier tubes that are widely used in radiation detection with silicon photomultipliers. And so what you see on the top right here is an example of for radiation detection. This is a scintillator with waveguides, and then you have an array of photomultiplier tubes down here at the bottom. And our goal is to replace these photomultiplier tubes with silicon photodetectors. And the reasons we'd want to do this is because their photomultipliers are relatively large in size. And so if you notice, these are the photomultipliers down here, and there's a lot of gap in spaces in between them, which means that you have to use these waveguides to be able to get your light from your scintillation material. It's expensive, relatively expensive. It's got a lot of temperature dependency. And for a lot of these applications, and so we're looking to use this actually in a beamline, there are actually very high magnetic fields which affect the photomultiplier tubes. And silicon is less sensitive to magnetic fields. And so there are a lot of reasons to use silicon-based photodetectors instead of your photomultiplier tubes. And so for all of these reasons. And so your silicon photomultiplier is based on the single photon avalanche diode. And so a single photon avalanche diode is nothing more than your PN junction that's operated in reverse breakdown. And so what you do is you bias your photodiode with a voltage that's higher than the breakdown voltage for the diode. And so when a photon comes in, it's going to create an electron hole pair. And because you have such a high electric field, you'll have impact ionization, and you essentially create an avalanche of current. And now this avalanche of current is going to have a voltage across this resistor, which will then lower the voltage across this single photon detector and bring it below the breakdown voltage, quenching the avalanche process. And so what you have for a single photon avalanche diode is this sort of digital response that you see over here on the right. Now, with our single photon avalanche diodes, or SPADs, so on the right here is a your left, my right, is a Centaurus simulation for a PN junction. And so what you see here is this is the electric field, and so this is our junction here, and so we've simulated an NWEL P+ diode in sort of a standard half micron process. And so what you notice is that you have these regions of red here where you've got sort of an increased electric field compared to the rest of the junction. And so really what happens is you get breakdown at the edges of your junction. And so this represents a reduced efficiency for your SPAD detector. And so there have been quite, a lot of people looking into how do we, prevent or mitigate this premature breakdown of your SPAD devices. And so one approach is to use what's known as a perimeter-gated SPAD. And so to do a perimeter-gated SPAD, you simply add a polysilicon gate over the top of your junction. And so you apply a voltage, and this will help make the electric field more uniform across your entire junction by simply so it modulates your carrier concentration just below here and helps to make that field a little bit more uniform. And what this does is it changes the breakdown voltage. So as we increase the voltage here, you can see an increase in your breakdown voltage for your PN junction compared to just a SPAD alone, and it actually affects the noise floor of your device. So you get a decrease in your overall dark current rate as you change the voltage on the gate of this SPAD. Now, your silicon photomultiplier is just going to be a parallel array of these SPAD devices. And so what you see here is this is our perimeter-gated SPAD. And so this is a regular SPAD with an extra gate terminal. And we use a PMOS transistor instead of a passive resistor for, you know, for space reasons, okay? And so it's just a parallel array of these. And so when your photons come in, you can have multiple of these SPADs actually give you an avalanche current, which is now then summed. So all of these connect at the top here, okay? So these connect, and these are actually connected to this node here as well. And so what you get is a sum of all your avalanche currents from all of these individual SPADs. And so the output of your silicon photomultiplier is an analog current, as opposed to a digital current of the SPAD alone. And so we've fabricated this device. So we did a sort of an 18 by, I think, 29 array of these devices. And so here, this is our perimeter gated SPAD. This is the gate area around it with our PMOS. And so the active area of this is about, I think, 12 by 12 microns, giving us about a 6% fill factor for this perimeter gated silicon photon multiplier, silicon photon multiplier. So we've characterized this device for noise and for spectral response. And so what you see here, okay, is we have a plot of our current versus the excess bias voltage. Now the excess bias voltage, so we bias we have a voltage across the diode and resistor that's beyond the breakdown voltage. And the difference between that voltage and your breakdown voltage is what's known as the excess bias voltage. And so that's what we've got on your horizontal axis. And so as a function of the excess bias voltage, what you see is that your dark current increases. And the reasons for this is fairly well known. The reason for this is fairly well known. So you're increasing your electric field, and you're increasing the drift velocity of your carriers. And so you get an increase in your noise floor as you increase this excess bias voltage. But the part that we really want to focus on is that how it responds as a function of our gate voltage. So as we change the gate voltage, and so this is the magnitude of the gate voltage that we apply, our noise floor actually decreases with the increase in that voltage. And so it increases fairly sharply for the first couple of volts, and then at some point as you increase the voltage, it makes a slightly less impressive impact on the decrease in our dark current here. And so the reason is the gate voltage actually decreases the probability of our SPAD responding, actually having an avalanche current. So this is a probabilistic process. And so it changes the probability that we will actually get a spike in any given SPAD. And so after doing our noise response, we wanted to look at our spectral response, see how this responds light over our spectral range. And so for that, we use a monochromatic light source where we can vary our optical power, we can vary the wavelength. We use an independent optical power meter to quantify our incident power at a given wavelength, and we use an integrating sphere and have some data acquisition to actually measure the output from our PGSPADs. So we quantify things actually in terms of the signal to noise ratio. For all of our experiments, we kept the optical power at 20 microwatts per centimeter squared. The reason for this, so this corresponds to about 10 to the 9 photons per second, was that when we looked at the data sheets for commercial silicon photomultipliers, they tended to report their optical characteristics in optical powers of this range. And so we decided to make our measurements in line with what is being offered commercially. And so your photon detection efficiency, which is a function of your measured photocurrent, this IM, your Planck's constant, this is just your speed of light. G here is the gain of your silicon photomultiplier microcell, which is your individual SPAD with the resistor. That's your microcell. And so this is actually related to our signal-to-noise ratio, which we can measure as just our current, our measured current minus our dark divided by our dark current. And so we quantify the signal-to-noise ratio as a function of our excess bias and our gate voltage. And so as a function of our excess bias, we see, so this is a wavelength, so we go across pretty much your entire visible range, and we see our expected peak at around roughly 500, and we see that in line with what has been published, that as you increase your excess bias, that your signal-to-noise ratio, which is similar to your photon detection efficiency, actually decreases. But as a function of the gate voltage, so again, we have our wavelength here, and this is your signal-to-noise ratio. And so these are for different gate voltages. And as we increase that gate voltage that we're applying, we can actually change the signal-to-noise ratio. And this is going from 0.1 to close to 1,000 here. So it's over a few orders of magnitude. We can actually change our signal-to-noise ratio for our silicon photomultiplier device. And so really what having that gate voltage did for us was allowed us to have a tunable device where we can change our signal-to-noise ratio. And this is important because remember that very first picture that I showed, I actually want to make an array of these silicon photomultipliers. So they're going to be independent arrays, and we want to be able to normalize the outputs from each of these detectors. And so this gate voltage actually gives us a way to normalize our response from each of these silicon photomultiplier detectors. And so in conclusion, what we did was we showed you a CMOS silicon photomultiplier based on these perimeter-gated single photon avalanche diode devices. So it was fabricated in a 0.5 micron process, and this one had 162 parallel microcells. We've shown you the spectral response at a single power for this particular paper, but we have actually measured it over a range of optical powers. So we fully characterized this silicon photomultiplier-based PGSPAD. And really the takeaway here is that this silicon photomultiplier has the unique feature of being tunable. So we can tune the sensitivity of the device and the response of the device by just applying different gate voltages to it. And so this is a promising method of being able to tune an array of these devices for our detection applications. So, thank you, and any questions?